So when we look at the rocket ship, okay, it talks about how the new rocket ships don't put out as much force. So how can such a small force create such a significant momentum? Well, like we talked about the other day with the airbags, for me to have a large change in momentum, I have to have a large impulse. So if I have a small force, the only way to have a large impulse and a large change in momentum is I have to have it over a longer amount of time. So instead of only operating a few minutes, it can operate for days, weeks, or months. Remember, when we talk about impulse, force times change in time equals change in momentum. So if I have a small force, I need to have a large time. So let's look at a problem. This one is in your book on page 248. So if I have an astronaut at rest, what's rest mean? If it's at rest, that means it's going 0 meters per second. Okay. Flies a thruster pistol, or fires a thruster pistol, a gun, that expels a quick burst of 35 grams of hot gas at 875 meters per second. The combined mass of the astronaut and the pistol is 84 kilograms. How fast and in what direction is the astronaut moving after firing? This is a recoil one. So they start, so I have the astronaut and his gun. Okay, right now they are stopped. They have 0 momentum because they are at rest, both of them. The bullet's at rest, the astronaut's at rest, the gun's at rest. But afterwards, that has to be equal to the combined momentum of both. The momentum of the astronaut and the momentum of the gas or the bullet that comes out of the thruster. So what's going to happen? Well, the astronaut is technically going to move backwards a little bit, right? Not very much, but think about recoil when you fire a gun, because the bullet is going to go out this way. So they're going to have equal and opposite. Okay, so the mass and velocity of the astronaut, final, plus the mass and velocity of the gas have to equal 0. Astronaut and the pistol, because he's still going to be holding the pistol. All right, so you need to convert. One thing that we notice is this is in grams, this is in kilograms. So we have to convert this into kilograms first, and you need to plug it back in. So this is going to, once it's in kilograms, is going to go here. This is going to go over here. The combined mass is here, and I can solve for this. Okay, work it out. You should be able to do it. Check your answer. If you need help, look at page 249, and I also have my answers in my binder that you can look at, or in the folder. Okay. So far, we've looked at the momentum in only one direction. Well, guess what? We can apply this to 2 dimensions too, just like we could to the force. So instead of it only being on one plane, like here and here, we can also have it in 2 dimensions, like our triangles. So the only thing that we have to do is we have to consider those extra dimensions. The law of conservation of momentum also holds true for other things as long as it's closed and a closed system and has no external forces. No matter which way it's going, as long as it's closed and isolated, it can work. So regardless of the directions before they interact. So it can work for objects in 2 or 3 dimensions. So billiard balls, pool balls. We're going to go play pool later when I get back. But think about pool balls. Is momentum going to be conserved? I hit the cue ball. It hits this ball and collides with this one. Goes off in this direction. This one goes off in the next direction. Okay, is momentum conserved? Well, after the collision, both balls are moving and have momentum. As long as friction can be ignored and it doesn't hit the walls, then yes, it is going to be closed and isolated, so momentum can be conserved. So we can use the law of conservation of momentum, which means the momentum before is going to equal the momentum after. But we're going to look at the components of the vectors. So the sum of the components in the x direction have to be equal, and the sum of the components in the y direction have to be equal. I'm going to look at my x components, and I'm going to look at my y components. And like we did last chapter, I'm going to break it apart. I'm going to look at the x separately, and I'm going to look at the y separately. Okay. They have to be independent. We can draw them, and we can look at them. So this problem is on page 250. Look in your book at page 250 to work this problem out. Okay, I have a car that's moving north at 27 meters per second. Okay. It collides with a car that's moving east. So they're going to hit right here at this point. Sorry, but that's the way they look at these problems. Okay. Now, what direction and what speed will they move off of? Well, logic tells you it's going to go off in this direction. Well, how much and at what angle? Okay. Well, I have to consider them in, first of all, I have to change my arrows so that they're head to tail, or tip to tail, and then I can find this one right here. Okay. Now I have to, first of all, I have to calculate the momentum of this car and the momentum of this car. And then I can go ahead and solve it with Pythagorean theorem to find this and use tangent to find this. Okay, so plug in your numbers, go ahead, find the x direction and the y direction, plug them in to use Pythagorean theorem, and find tangent. All right, the last thing, you can look at the practice problems that are in your book, please, and work them on the board. Look in the back of the book. The more practice you do, and then we'll come back and I'll do practice when I get back. The last thing that we have to talk about is conservation of angular momentum, because it too is going to be conserved. Okay? Whether it's linear or angular momentum, it's conserved. So the law of conservation of angular momentum states that if there are no net external torque, remember is forces in a circle, that acts on an object, then its angular momentum doesn't change. This is the equation, but you know what? We're not going to do any math with this. We just want to understand the concepts. So we're not going to work on this math stuff, okay? But its initial angular momentum is going to be equal to its final. So for example, the Earth spins on an axis with no external force. So its angular momentum is going to be constant. Therefore, its angular momentum is conserved and the length of the day does not change. But think about an ice skater. Okay? An ice skater pulls in his arms. He begins to spin faster. Okay? Once he was already spinning, he didn't need to give him any extra force, any extra torque. All he had to do to spin faster was bring in his arms. Okay. Without an external torque, his angular momentum doesn't totally change, but he can change his velocity by changing his moment of inertia, his angle of rotation. So by pulling his arms closer to the body, brings him closer to the mass, or his mass closer to the axis of rotation, decreasing the rotation, or the radius of rotation, therefore decreasing his moment of inertia, and it can increase its angular velocity. The moment of inertia is like its mass, and its angular velocity is like its velocity. If I increase one, I can decrease the other to end up conserving momentum. If a torque-free object starts with no angular momentum, it must continue to have no angular momentum. So if part of the object rotates in one direction, the other part must go in an opposite direction. For example, if you switch on a loosely held electric drill, The drill body will rotate in one direction, opposite of the rotation of the motor and the bit. All right. So we will come back and talk more about that when I get back. Do the best that you can. Practice your problems. Read through it. Look at the examples. You can work together on the worksheet that you have on Tuesday, I think. No, Thursday, I think. And you can do some problems on the board. Talk with Mr. Panner for my examples and do the best you can.